Hello, my name is Rohan Sharma and I am delighted to present my research work titled as Fabrication of Flexible Diode using Screen Printing Technique. Let me introduce you to my research team, my mentors Dr. Om Prakash SS, Senior Researcher, and Mr. Adarsh VN, Research Associate from Department of Physics at Prayoga Institute of Education Research, Bengaluru, and my friends Mr. Manish Nukavrapu from the Hyderabad Public School, Begumpet, Telangana, and Mr. Mukunda P. Bharadwaj from Samvida, Bengaluru. So let's understand what is flexible electronics. So flexible electronics are the electronic devices and circuits made on a bendable and stretchable materials instead of rigid silicon substrate. They use conductive inks, nanomaterials on flexible surfaces such as plastic, paper, or fabrics, allowing the devices to bend and functional normally. This technique is widely used in wearable devices, flexible displays, medical sensors, and smart textile due to its lightweight, portable, and its low cost nature. So, the growth of the flexible, lightweight, and the cost effective electronic devices has surged in recent years in many areas such as wearable technologies, healthcare products, intelligent packaging, rather than those rigid silicon based devices. Flexible electronics overcome this by printing functional material on a bendable substrate, enabling lightweight, low cost, and stretchable devices. This work focuses on the fabrication of p-n junction diode using the screen printing technique, demonstrating a simple, low cost, and a scalable approach for developing the flexible electronic devices. So let's understand what is the screen printing. So screen printing is a low cost, versatile method compatible with a large area roll to roll manufacturing when compared to other techniques like inkjet, gravure, and flexographic and or aerosol jet printing and scalability or material compatibility. Let's understand the methodology of the process. So, firstly, we have synthesized the metal oxide, then we have prepared the inks, followed by the diode designing and the diode fabrication process. So, to synthesize the metal oxide, we have firstly synthesized a zinc oxide using the hydrothermal method. We have used zinc acetate as our precursor material, and you can see in the all the steps followed here, and we have also done the centrifugation along with the washing and drying for the 6 to 7 hours at 80 degrees Celsius. And after completion of all the processes, we have finally got our zinc oxide nanoparticles. Now, the synthesis of copper oxide, we have done the chemical precipitation method with the CuCl2.2H2O plus ethanol as a precursor material, along with adding the 5 molar NaOH drop wise into the solution. So while we are adding, we have noticed some changes, some color changes from green to bluish green to blue to black, which indicates the formation of CO nanoparticle. The same process of washing and drying has been followed, and the final product, our copper oxide, has been obtained. So now let's talk about the preparation of inks. So we have firstly prepared the ZNO ink. So we have used the 38 weight percentage of isopropyl alcohol IPM as a solvent and 12 weight percentage of polyvinyl pyrrolidone PVP as a binder material. We have made the solution, and then into that we have added ZNO as a functional material, and followed by the mixing, sonication, and the final mixing process for 30 minutes, 10 minutes, and 10 minutes respectively. So the composition which we have followed is 38 is to 12 is to 50. So we have gone for this composition because there are many key benefits for this. Though one of them is the uniform dispersion. We are getting the uniform dispersion while fabricating the diode. The inks are stable at the room temperature and they are suitable for screen printing. The same solvent and binder has been used for preparation of the CO ink. Even the same steps we have followed, and the same composition 38 is to 12 is to 50 has been followed for preparing the CO ink, and we are getting a stable CO ink. Now let's talk about the diode designing part. So let me explain about our diode design. So on first we have our top electrode, which is silver. Then we have our p-type material, which is CO, and below it we have our n-type material, which is ZNO. And at last, as a bottom electrode, we have the carbon ink. So firstly, we have coated the carbon ink on a glass slide using the doctor's plate technique. Then I'll explain you our layered deposition process. So we have our bottom electrode as a carbon ink. Then we have coated the ZNO ink as our N type using the screen A, as you can see here. And then we have cured it on a hot plate. We have then on top of it, we have printed a CO ink as a P type and cured it under the same condition. So this formed the PN junction. So to make the junction in a contact, we have coated the silver ink as a top electrode on top of that using the screen pre, as you can also see here. So after coating all the inks and fabricating the device, we have just kept it for drying for some days, and after some days we have peeled off the bottom electrode layer and a flexible device has been obtained, as you can see in the picture. Now, let's talk about the results and discussion. So, as we have carried out the X-ray diffraction to know the crystal structure of the material, so for ZNO, as you can see, there are prominent peaks at 100, 002, and 1001. It matches and agrees with the ICDT database and confirms the hexagonal structure of ZNO. And say for same for the CO, we have a peaks at -111 and 111. It also agrees with the ICDT database stating the monoclinic structure of CO nanoparticles. We have done the UV visible spectroscopy. So for ZNO, you can see there is a sharp absorption peak at 369, which is a characteristic of a ZNO. And you can also notice there is no peak between 300 to 450. This tells the high purity of ZNO without any significant impurities in it. So it indicates the characteristic of ZNO. Now, for the same, we have CO nanoparticles. We have seen the absorption peak at 251, which is also the characteristic of CO nanoparticles, and it confirms the presence of CO in it. Now, let's talk about the band gap. We have done the UVDR spectroscopy along with the using the Kubilka-Mann function and Tox plot, and we got our band gap for both the materials. We got 3.16 electron volt for ZNO and 1.93 electron volt for the CuO. Now, let's talk. We have also done the Fourier transform scanning electron microscopy to check the morphology and size of the material. So for ZNO, they are just self-assembled into hierarchical flower-like porous structure with the broad size distribution, size ranging from 26.6 to 486.7 nanometer. And for CO, we notice there is a uniform quasi-spherical morphology with a size ranging from 5.5 to 146.5 nanometer. We have also done the Hall effect, so on some parameters. So as you can see, so we have done the Hall effect to check the semiconducting behavior of the material. So the RH value tells the type of charge carrier it is. So we have a positive RH value for CO, so it indicates that it is a P type, and we have a negative RH value for ZNO, it is a N type. So we have also done some other parameter, which is carrier density. You can see it is 4.76 into 10 to the power 15 for CO and 5.8 into 10 to the power 14 for ZNO. And next we have mobility. Mobility is 129 centimeter square volt per second for CO and 657 centimeter square volt per second for ZNO. We have also done the resistivity. The resistivity for CO is 10 ohm centimeter and for ZNO is 16 ohm centimeter. At last, we have done our IV graph analysis, and this is the graph for our normal device and the flexible device. You can see our knee voltage for the normal device is around 0.9 volt, and for a flexible device, it is 0.8. Indicates we have successfully fabricated the diodes, and it is as efficient as the normal device. So, we have concluded our research by successfully fabricating a PN junction diode using a screen printing as a low cost and scalable method. ZNO N-type and COP type ink deposited with a silver top and carbon as a bottom electrode. We have also achieved a flexible device by peeling off the bottom electrode from the glass substrate. There is a uniform ink deposition via screen printing. We have done the IV characterization which confirms the ideal diode behavior. So the future scope for these studies is we can fabricate more devices for and establish repeatability We can conduct rectification efficiency test. We can also investigate noble metal oxides combination to enhance the performance of the device and the uniqueness. We can also explore the biodegradable substrate to align with the fabrication with sustainable and eco-friendly practices. And we can extend the study to access the performance stability under the mechanical stress, ensuring the reliability for the flexible electronic applications. So, at last, I'd like to thank Prayoga for providing me the opportunity, facilities, and the laboratory support to carry out this research. I am also grateful to my mentors, Dr. Om Prakash SS and Mr. Adarsh Swain, for their valuable guidance and the continuous support throughout the project. I'd also like to thank my all the sponsors for the generous contribution which helped me, they made this work possible, and a special thanks to Center for Nano and Soft Materials for characterizing a metal oxide sample and providing the technical support for the study. Thank you so much.